Hello, my name is Christiana Ade, and I'm a fourth-year PhD student getting ready to graduate this summer at the University of California, Merced. And I'm really excited to present to you today about a recently accepted article in the Journal of American Water Resources Association entitled Assessing Fish Habitat and the Effects of an Emergency Drought Barrier on Estuarine Turbidity Using Satellite Remote Sensing. Deltas are home to 500 million people worldwide. They support some of the most productive agricultural regions and provide critical water resources. However, many deltas currently face risks related to rising sea levels, sediment loss, and droughts. Droughts in particular impact the delicate balance of freshwater and saltwater, thereby potentially harming the ecosystem services we humans depend on. The Sacramento-San Joaquin Delta is one of many deltas facing these threats. It is the hub of California's water system and provides $5.3 billion of economic output and is a hotspot of biodiversity by providing habitat to 50 endangered and threatened species. Some of these species include native fish, such as delta smelt, longfin smelt, and Chinook salmon, all of which are currently experiencing a rapid population decline due to many factors, including changes in water flow and water quality. In 2015, there were record low catches for all three fish, and in particular for delta smelt. Droughts are a major driving force behind these declines, and in 2012 through 2016, California experienced one of its deepest, longest, and warmest historical droughts. Past and future droughts remain a key consideration in California's water management policies and infrastructure. In spring 2015, the height of the drought, the California Department of Water Resources dropped 15,000 tons of rock into False River in the Central Delta to halt encroaching tides that had little fresh water to hold them back. This was named the Emergency Drought Barrier. And a few months later, it was clear that the barrier worked, as salinity rose on one side and fell on the other. But what were the effects on fish habitat and other water quality parameters? Potential changes as a result of barrier installation were previously studied and reported conflicting conclusions regarding impacts on turbidity. These conclusions were drawn mainly from point-based data sources such as continuous monitoring stations and discrete sampling. We wanted to expand on these point-based studies and evaluate what high-frequency and high-spatial resolution information could provide about the impacts of drought related to turbidity. As a precursor to the Sentinel-2 satellites, CNES, CESBio, and ESA partnered to create the Spot 5 Take 5 experiment, which provides imagery from April 16th to September 8th of 2015. The Spot 5 satellite was deorbited to mimic the 10-meter spatial resolution and 5-day repeat period of Sentinel-2. This was an experimental dataset created so that researchers could establish methodology and workflows prior to Sentinel-2's launch. And while Sentinel-2 is now in orbit, the Spot 5 Take 5 experiment provides the only open-access, high spatial, and high temporal resolution satellite data during the 2015 drought. We used this data in two case studies to demonstrate how such data could be used to support management-relevant scenarios related to turbidity. The main research question of one of our case studies was, what was the impact of the barrier on turbidity? To answer this question, we created a time series of turbidity maps in units of NTU by applying the Merced algorithm and performing a study site calibration using in situ NTU measurements. If you think back to the slide at the beginning of the presentation, where there were stations spread out throughout the delta, you can really see how satellite observations actually fill in these gaps between stations and provide spatial information. We then compared two pre- and post-barrier image pairs with similar tidal conditions, one for a flood tide and the other an ebb tide. We calculated the mean turbidity in 4 areas near the barrier location that were previously identified as areas of potential concern. For the flood pair, we detected minimal difference in turbidity between pre-barrier and post-barrier images. However, for the Ebb pair, we detected an increase of 6.6 NTUs in the San Joaquin River and an increase of 4 NTUs in a small channel called Fisherman's Cut. This difference is also apparent in the pre and post images for the Ebb pair. The San Joaquin River is colored light to dark blue, indicating about 8 NTU, and the post is a bright green color, indicating about 15 NTU. And we can very clearly see the difference in spatial context. This provides additional supporting evidence that any changes detected in previous studies with point measurements were not just a result of local sediment resuspension near the sample site. The second question that we used these turbidity maps to answer was, what was the habitat extent of endangered fish during the drought? We chose to focus on the habitat of delta smelt because several water management decisions require maintaining turbidity at 12 NTU or above, since below this threshold the delta smelt experience extreme stress. We use this threshold to map frequency of suitable turbidity. Green indicates low frequency and brown high frequency. And we found only 5% of waterways were suitable for greater than 60% of the summer. And even though we identified 3 areas of potential suitability, these areas were infrequently connected. When we overlay actual fish catches on our frequency of suitable turbidity map, we can see that in most places they align. Our maps also show limited connectivity between the southern delta and persistent smelt refugia, which may indicate why delta smelt are rarely present in this area during summer months, and shows that despite concerns, fish may not migrate close to water pumping stations. However, the potential extended area of suitable habitat in the San Joaquin River as a result of the drought barrier, potentially, may be of concern because the fish that travel downriver could get trapped in reverse flows and become entrained at the water pumping facility in the south. However, retrieval uncertainty has consequences for the amount of potential habitat detected, and you can see that the minimum and the maximum maps show very different areas of suitable turbidity frequency. This is motivation for researchers to continue to improve satellite retrievals of turbidity at lower values. Looking beyond the drought, Spot 5 Take 5 and the summer of 2015, with investments from NASA's Applied Sciences program and in partnership with the CA Department of Water Resources, the Metropolitan Water District, Oregon State University, JPL, and UC Merced have extended this turbidity mapping to Sentinel-2, creating an operational turbidity monitor that managers can use to support decisions about gate and pumping actions that meet obligations to manage for delta smelt and can compare the remote sensing maps against in situ stations managers have traditionally relied on for such decision making. So what I'm showing here is just an animation of the web app on Bay Delta Live that I'm talking about. We are also working to expand the effort to include other important habitat variables, including temperature, since the smelt habitat is not only dependent on turbidity. Plotted here are surface temperatures from Landsat, which is a reasonable predictor of bulk water temperature observed at SeaDeck in situ stations. So on the x-axis, in situ measurements, and on the y, Landsat measurements. Recent studies have quantified the critical thermal maximum temperature of delta smelt and several other invasive competing fish species. And it is shown that the maximum tolerance for delta smelt is 28.6 degrees Celsius. In collaboration with Christine Lee and Gregory Halverson at JPL, our next step is to expand the suitable habitat mapping approach to consider both temperature and turbidity using the Landsat record, the new ecostress sensor, and Sentinel-2. In conclusion, high spatial resolution, high frequency satellite remote sensing can be used to aid management decisions. And this addition of spatially continuous data to in situ monitoring efforts enhances management decisions by providing spatial context and regional scaling, enabling users to sample any area rather than rely on point measurements, and provide measurements for areas with limited or no in situ data. If you have any questions about the research that I presented, feel free to email me at cade@ucmerced.edu.